Thank you very much for inviting me to this workshop, and thanks so much for holding this workshop, which is, I think, a milestone each time it happens for event-based vision and neuromorphic computing. So I thought that by this time at the workshop, someone will already talk about neuromorphic computing hardware and present it, and that didn't really happen, and I think that's telling. Yeah, so event-based vision sensors and neuromorphic computing hardware are kind of siblings. You know, they were born in the same lab. They share the same DNA of event-based spiking representation of signals. And it should be obvious that neuromorphic hardware should enable amazing performance in event-based vision applications. Because there's such a nice match between representations. But it seems that we are not quite there yet. So in this talk, my main goal would be to see where we stand now, what has been tried in neuromorphic hardware, mostly in our Intel's neuromorphic hardware, in our Intel neuromorphic research community in terms of event-based vision, and what is maybe missing, what is the path to the future. To set the scene, there are people call neuromorphic hardware very different things, right? So our Loihi neuromorphic chip is a digital device that simulates spiking neurons. There are a couple researchers here who have developed mixed signal devices, and there's a whole community that builds devices based on new materials like memory assist technology. So to agree, at least for this talk, like what is neuromorphic computing hardware, I would maybe emphasize three components. The first is the neuronal model. And the neuronal model, of course, has spiking character of exchange of signals and information between neurons, similar to event-based camera. So we exchange information with spikes or events. And the second component of the neuronal model is the temporal character of processing. So in each neuron, we have temporal filter on the internal dynamics of the neuron. So activation is not just number, it's number that develops over time. And we also have some temporal filtering on the synapse. And in today's hardware, these temporal filters are fairly simple, right? We have leaky integrating fire inside the neuron. We have some decay usually, or some delay, fixed delay on the synapse. This maybe could be done more in a more complex, more powerful way to increase the power of neuromorphic computing, something that Riyad mentioned that might be needed. So first, the neuronal model. Second, the network topology. So when we think about neuronal networks today, we have this picture, with layers and layers of feed-forward processing, convolutional or fully connected, but usually feed-forward networks. Neuromorphic hardware allows us to wire up whichever network we want. Right? We have a bag of neurons, we have connections between them. So the space of algorithms that we could implement in this hardware is immense. Right? We can come up with many different structures and implement many different algorithms. The big question that I will try to illuminate in this talk is how to build those algorithms. We have deep learning, but do we have anything else? Is the question. And the final distinguishing characteristics is learning. So learning in neuromorphic hardware is biologically inspired. In biology, neuronal networks seem to use these local learning rules so that every synapse in the network can change, but this change is only informed about two neurons that the synapse connects and nothing else in the network. So if you have some optimization-based learning technique, you have to make sure that you can break down your learning process to these local learning rules if you want learning to run natively in neuromorphic hardware. So at Intel, we have developed the neuromorphic research chip Loihi. It's not a product, it's a research chip with different form factors. And for this community, the most interesting is probably the smallest one, a USB stick form factor device with 200,000 spiking neurons. So you can estimate the size of the networks you can build there, which has a direct address event representation interface with which you can connect event-based sensor to it so that you don't have to go over a computer before you get to actual neuromorphic device. And then we have some larger systems, and there are new systems are being developed. So the big question, what does it take to enable event-based visual processing on neuromorphic hardware, right? So we have our events, and then we have these neurons, they have their internal dynamics, their spikes. How do we let them do something useful? And then this is the full list of methods that I could think of while looking at the work that has been done on Loihi so far. Deep learning is, of course, the first thing people try because it's so powerful in conventional vision. And you can apply deep learning by pre-training your network as a conventional deep network and then converting it in a spiking neural network. You can also do deep learning directly in spiking domain. I mentioned it briefly. You can design spiking neural network-based versions of some other algorithm. take your favorite optic flow algorithms or some segmentation algorithm, and one could find a spiky neural network version of that or equivalent. And many of these algorithms could be, some old or maybe some completely new algorithms, which we never thought of because we had our conventional computers in front of us that have certain constraints and certain things run faster or slower. So as I mentioned, the space of algorithms is really huge. One can also do direct search of network structures using, for instance, evolutionary optimization, and maybe there will be a talk on this topic in this session as well. So that if the network is not too large, you can probably find an efficient structure that will solve your task just by searching the space of network structures. Or one can just get inspired by biology. In neuroscience, people have discovered many circuits in different animals, often in some small animals like insects, locust motion detector, giant motion detector neuron, or in bees or in flies, have discovered different structures that solve some tasks. And one could port these structures, these algorithms to neuromorphic hardware and by that make them do something useful. I will stop a little bit on this slide and then I'll go through the other ones very quickly. So deep learning in spiky neural networks is the first thing that people try to do, because today you don't really want to design those algorithms. You have your data, you want to train something and let the network discover the structure that's needed to solve your task. And there are three ways how you can apply deep learning on spiky neural network. The first one is training conventional artificial neural network with a backprop, and then converting it into spiky network, mapping it on Loihi. One can do that. One won't lose much in accuracy if one does that right. Sometimes you have to take constraints of the hardware into account when training the network. That helps. And when people do that, then usually they use so-called rate encoding, so that the values of neuron activation, all those numbers, they will be represented as firing rates of neurons. And you can see how that is not the best way to do things. So first, your neurons then have to fire a lot. They have to fire like crazy if the value is large, and they have to fire once in a while if the value is small. They also won't be the fastest network, again, because you have to sample these different rates. So you have to wait for your slowest rate to emit a spike. But this is the first thing that people try. And it's a bit dangerous to conclude about the power of neuromorphic hardware based on this approach. One can use training directly in spiking domain. What you do there is that you take your temporal structure of the signal very seriously. So your temporal structure of the signal should then matter for your task, because what in many of these networks, for instance, Slayer, which is training with surrogate gradient, where you train both weights and delays. So your network will be fine-tuned to the particular temporal structure of your signal. And then usually you would use spike timing for representation of information. So it won't be rate of neurons, it will be the special temporal patterns of spikes. And the third thing that you can do is pre-train the network with either of the two ways, and then leave some place for using that on-chip learning, that local plasticity that we have on the chip. And if one does that smartly, then one can develop quite powerful networks. I will just flash a couple examples. Most of you probably know them, right? With Slayer, the first example that has been done is training the network to recognize gestures. The DVS gesture data set. So I think it's notable to remember here that Slayer learns the special temporal structure of this task. So the temporal character of all these events is important and can generalize because, of course, many of the events are noise. One has tried to combine vision with tactile perception and then learn association between the two on chip, again, using online on-chip learning. One has tried to take that pre-trained network for gesture recognition and then make the last layer plastic. So introduce additional output head for the network that will be trained on chip with local plasticity. And so in this paper, it has been shown how a new gesture can be added to the list of the gestures that you had in your data set. And this, of course, needs to respect constraints of the usual continual learning, right? So your second to last layer needs to be representative of this new gesture that will come. It cannot be something completely wild. Now, is deep learning the only thing you can do? And you might guess not. So I will show this example here, although it hasn't yet been applied to event-based data, it has been applied to images. But one visual task that can be solved without deep learning, rather be solved with something like k-nearest neighbor search, is the task that we solve when we do place recognition in SLAM. Right? When we travel around the environment, we store different views that we have encountered on the way. And then when we see some view, we want to immediately find a match in a long list of memories that we have stored on the way. So, place recognition. So we have shown in our larger Loihi system, one can solve this type of task very efficiently. And the trick is, so you have your image or you have your event-based representation. You find a way how to efficiently encode it on chip. And here it's efficiently encoded by using first sparse coding. So you use features that allow you to represent your image in sparse vector. And then additionally, you represent this vector in a spatial temporal pattern of spikes. So the values are represented in the timing of spikes. So you have a very compact representation that can be stored efficiently on chip, again, with delays and waits on chip. And you store many such patterns on chip. Do I have not too much time?
Yeah, 1 minute. Yeah. Can you start
1 minute?
Up?
Okay. I'll just show how efficiently this we can make a big jump. So if you have stored 1 million of such images and now you want to recognize a new one, you can immediately stream this new image to the thousands or millions of other images already stored and immediately get the result. So what I show later, continual learning is very important. We can make good use of that plasticity on chip if we enable autonomous learning. And to enable this autonomous learning, we have been designing neuronal state machine that kind of orchestrate processing in the spiky neuronal network, kind of switching between training and learning phase. This just flashes that you need more than just object learning or recognition. Usually in many tasks, like for instance, in the robotic learning task, you also need to control behaviors of the robot. You might want to form some spatial representations. And your hardware can help you to have very fast vision for control. So in the end, like one vision could be that you can have full processing done on chip. I will spend maybe 20 seconds on these slides because that's important. You can look for more details in a recent IEEE proceedings paper that we have published. And this paper shows how well different workloads run on Loihi compared to other hardware. And it shows us in terms of energy advantage and solution time advantage, Loihi versus other hardware. And we can see that all those deep learning converted networks that use rate code, they all land somewhere in this corner. So sometimes you have some advantage, but usually not much. And in this corner where you get 5 orders of magnitude advantage in terms of energy and 3 orders of magnitude in terms of time, there we have these other types of algorithms. It's either some recurrent neural networks like controllers or some sparse coding graph-based networks, k-nearest neighbor search, different SLAM algorithms or constraint satisfaction problems. Yeah, the challenges. So develop the algorithms for hardware. Why don't we hear many talks about vision algorithms running on hardware? Because developing algorithms there is a real challenge. Benchmarks, I think, is a challenge for all of us, and all the tools, libraries, software, user interfaces that we are just lacking. And to comment on Riyad's comment, computing hardware is not really set in stone. So I think we are still in this learning phase where we want to learn from trying to use this hardware in different applications, what needs to be changed and adjusted. To go beyond even copying the brain. So I think copying the brain and understanding it better is great, but maybe we can even go beyond. All right. Yeah, listen to the talk for the rest.
Yeah, thank you very much, Yulia. That was quite a good summary. Yeah, next one in the line, it's Samsung. So we have Anthony Bisulco and Volkan Isler as representatives.
Yeah, thanks. I'm going to share my screen. Oh,
I hope you can just take over control.
No, I need you to stop sharing at least first.
I did it.
Oh, there we go. Thank you. This screen. Good. Oh.
I have a question for Yulia. No, it's too late, or
it's too early, I think.
Okay, I'll keep it for later. Sorry.
Could you write it on the chat too, so that we don't forget?
I will absolutely do that. Thank you. Sorry.
Thanks.
All right, I'll start out then. So hi, my name is Anthony Bisulco. I'm one of the event-based camera researchers at the Samsung AI Center, New York. Today I'm going to be talking a little about high-speed perception action systems with event-based cameras. So going over briefly about the Samsung AI Center and some of the stuff we've been working on. So this is our AI Center in New York City. We're located in the Meatpacking District. In the top left here, you can see our lab space. We have a pretty big lab space. We have motion capture system, a variety of robot platforms, some great views, and great office space to work together. You can see some of the things we're working on and some of the things we're thinking about here in our Samsung CES presentation from 2021, where our President Sebastian Sung goes over some of the things we're thinking about in the future in terms of how we can have robots in possibly kitchen environments help us out with daily tasks such as preparing the dinner table, pouring wine, and a variety of other tasks. So we have a lot of work working on these sort of foundational AI issues, perception issues, lots of different tasks within this. And this is sort of some of the motivations behind our center, and we have research doing various parts of this pipeline. Just going over quickly one project that we've been doing before we go into the event-based risen research. This is some of our research on picking and placing and clutter. So you can see here we have a cluttered scene. We're going to pick an object, and from that we're going to pick this up. We've done some novel research in each of these sort of aspects here, from perception to motion planning to the actual action that's occurring here, and tried to put this together into a really nice demo to show you guys. So this is one of our projects. Now jumping into some of our event-based camera research, we're going to jump into one of our first projects, which was near-chip dynamic vision filtering for low bandwidth pedestrian detection. This was done along with some of my great co-authors you can see down here below, some of them in the audience today. So going over the problem there we were interested in, the things we were thinking about was we wanted to sort of apply DVSs to IoT systems. And one of the things about IoT systems is just the low bandwidth stream you need. If we're thinking about networks such as LoRa or other wireless standards that could have some long range interface, we need this low bandwidth stream. And if we want to pair DVSs to these low bandwidth networks, we need to think about two things. One, which was coupling this with some basically event stream compression that could basically sparsify our event stream so that we could use this. And then for our example application, we looked at pedestrian detection. So we looked at pairing this compressed event stream with a binary neural network to use the binary events along with binary weights to do very efficient inference on the entire process end to end here. So we invented some algorithms overall to sort of do this near chip. So we'd have basically a little algorithm that is first removing some of the noise in the event stream. You're seeing here a pedestrian walking around. You can see how noisy the event stream is originally. We then sort of do a coincidence detection operation, which removes this first noise, aggregation, which gets us to a normalized thickness of edges, and then a subsampling / coding, since we don't really need the full spatial resolution to do simple tasks like pedestrian detection in our example here. We implement this entire operation onto an FPGA, at least this denoising step and aggregation. You can see some of our steps here going from the event parser to, we show a UART interface here. This could be going onto a LoRa network or anything else that you would want to switch this out for. And then we pair this then with a binary neural network to do pedestrian detection or classification. We ran this on a microcontroller, the actual binary neural network. So in some sense, you would have your event stream compression occurring near chip. This would go off onto some IoT network. We could receive the stream and do inference on this in whatever edge compute you want to have there. So this showed that our filtering module was good for reducing the bandwidth overall in terms of the entire stream here, removing the noise, aggregating edges, subsampling, applying some Huffman coding, was very useful to sort of match these for IoT networks. And then also we were able to increase our testing F1 score in terms of our pedestrian detection performance by doing this denoising. So one of the things we think about in the future is we can integrate this onto possibly a DVS ASIC, improve the compressor performance, or possibly integrate multiple sensors so that we could have a better sort of simulation here on platforms of using multiple DVSs. So this was one of our first sets of work looking at near chip pedestrian detection. Our second set and sort of the main idea of this talk was sort of fast motion understanding and spatial temporal networks and dynamic vision sensors. So we looked at the problem here of trying to do rapid motion estimation in dynamic environments. So this could be a quadcopter, which is in a forest, and you need to avoid debris or you need to avoid incoming obstacles. This could be in a kitchen environment where we want to understand possibly chef's motion very fast, or we want to understand the things that are occurring around us to possibly react with a robot arm to do possibly a similar motion. This could be an autonomous driving scenario where we need to avoid incoming obstacles or cars around us. So we looked at this problem of high-speed motion understanding, and the first sort of sensors we can grab out there are active sensors. So sensors that send out some signal into the environment, receive these returns to perceive the environment around us. We're showing you here an example of an Intel rail sense with the right, where we have a flying dart approaching the camera. And just due to the spatial resolution of this sensor, we're not actually able to resolve out the flying dart in this example. But the main point we're trying to show here is the fact that active sensors, they do have some power utilization due to high power utilization due to sending an active signal into the environment. As opposed to a passive sensor, for example, like a DVS, where we can, here in the bottom right, I'm showing the same flying dart approaching the camera, and we're able to track this through time, resolve it out, and afford us these very low energy properties, but also great sampling properties for understanding this motion. So we look to biological motion understanding to sort of draw inspiration to how we actually do this motion understanding. Animals use visual cues to see what they should do in terms of planning escape behavior for a looming obstacle. For example, an object could be increasing in size in your visual field. This produces some looming response, and from this looming response, you want to plan some escape behavior. To model this, we looked at trying to inspect spatial temporal patterns in the event stream so that we could do very efficient avoidance maneuvers. We collected a data set, which you're going to see here, of a toy dart, which is going around 16 to 23 meters per second, approaching our event-based camera. And we looked at trying to perform an avoidance maneuver and trying to understand this motion overall. We also collected a ball data set you can see down here on the bottom. And to actually then try to understand this motion, we tried to model our algorithm in a few steps. So the first step, we acquire our XY polarity and time. We try to encode this to a set of, basically, we're trying to encode the history here of events. And we do this by a set of exponential filters. So you'll see down here on the bottom, these are exponential filters which look over basically a smaller time window. So you'll see very short portions of the motion, as opposed to the filters on the top where you can see the longer trajectory of the dart. And we're hoping that this encodes the various temporal properties of the event stream. And what we want to do next is we want to extract spatial temporal features from the filtered event set using a convolutional neural network. And I'm showing you here an example of some of these spatial temporal features. We then try to extract and estimate the time to collision and collision location in a supervised manner to then figure out, all right, you have 50 milliseconds to avoid an incoming obstacle, and this is the direction you should move. I'm going to show a quick example of now, this is an example of our testing set. So you'll see here in the top left, this is a log polar grid where we estimate the impact location. The red is the predicted location, and the green is the actual location where the dart is going to hit you. The next you're seeing is the incoming dart in the DVS event stream frame. To the top right, you're seeing the filtered probability estimates of the impact location. The bottom left, you're seeing the instantaneous estimates of these probabilities, and then finally the time to collision. Our next step, and one of the big things we looked into this system, was really understanding the latencies of the entire system. So we tried to measure basically when the dart began flying, when the dart actually hit the DVS, and how we did this was we had an LED photocell to measure when it left the, when it started flying, and then when it actually would hit the DVS, it would hit a glass with an accelerometer. So we have a full observability here in terms of when the dart begins flight, when the dart ends flight. We collect some events using our processing scheme here. We have an event-based algorithm, which I'm going to show you in a second. We're just doing simple tracking here. And then we have a motor command to say, move left or move right to avoid the incoming obstacle. So showing you this now happening in real time. This whole motion here is about 150 milliseconds. So we're really looking to push the event-based cameras to understand this fast motion and react to it. Showing you another example of this now in slow motion. So you'll see the DVS is down below. We have a target and we're trying to avoid the incoming dart. So this is, you see the slowed down example here, but again, it's 150 milliseconds, pretty fast motion overall. And we're looking to do these very fast sensing, perception, and action pipelines with event-based cameras. So wrapping up my talk, some of the things we found important in these systems, one was determining the right optics you need for the setting, determining what's your minimum resolution for a dart approaching and what you need there. Another important thing was the action latencies remain a large component of the end-to-end system. And some of the things we're thinking about towards the future is improving our terminal state estimation system, thinking about ways we can do this in a faster manner, evaluating some predictive methods to actually figure out where, for example, an obstacle is going, and then some unsupervised methods for perception. So that's wrapping up a little bit of our talk. We are hiring at the Samsung AI Center, so you can check out some of our job postings online. Thanks again for inviting us to this workshop. And if you have any questions, feel free to check out our talk there, or you can see our email down below. Thanks again.
Thank you very much, Anthony. That was right on time. And our next speaker is Guido. Guido de Croon from TU Delft.
Okay, thank you very much as well for inviting me today. Let me minimize this. I hope you don't see it. And let me get started. So I'm indeed Guido de Croon. I'm full professor at the MEV lab in TU Delft. And I'm going to talk to you about tiny drones. So the first one you're going to see is one that's going to fly into the screen now. It's the Delphi Nimble. It's a special drone because it flies like fruit flies do, or like any flying insect, by flapping the wings, but also by changing the wing dynamics when making a special agile turn. And we think that these drones can lead to new applications like tracking stock in warehouses or monitoring crop in greenhouse, because they're very safe, very lightweight, and they can actually still fly pretty far. But of course, they have to fly completely by themselves. Now, you may realize that this is very difficult because these drones in general are restricted in terms of size, weight, and power, and these drones even more. So this particular drone has a 33 centimeter wingspan, weighs 29 grams, uses 6 watts to hover, and has a tiny microcontroller on board, an STM32F4 with 192 kilobytes of memory. So that's really not much. And what does that mean for autonomous operation? Well, first, it means that the most successful approach to autonomous navigation, simultaneous localization and mapping is actually out of reach for these kind of drones. So SLAM typically takes around hundreds to thousands of megabytes of memory. And I made it red here, and also the 192 kilobytes, because there's quite a big factor of difference here, and we simply cannot do that. Now, you might say to me, okay, Guido, then get a better processor, right? So let's have a look at that. So this is actually a processor that's considered pretty small form factor, NVIDIA Jetson TX2. It has indeed a lot of computation, actually 6 cores CPU and 256 core GPU, 8 gigabytes of memory, so that's beautiful. Only it weighs 85 grams, so it's 3 times as heavy as the robot roughly, and it consumes more power to calculate than we need to fly. So obviously, we cannot just put this processor on there. And this kind of leads to kind of like a grim story, right? So are we just not able to make these drones autonomous? Well, we actually are. And the thing that we do is we draw inspiration from nature. And you can get really a long way with that and still work with microcontrollers, to be honest. Because the nice thing about nature is that evolution has found very elegant solutions to complex problems. And so you typically don't need to calculate that much in order to still succeed in successful behavior. But we do think that if you, in the end, go to high dimensional processing of vision, but even if you think of insects, like all the hairs over their body, then I think we do really need neuromorphic sensing and computing to make the next step with these small autonomous drones. And our goal is fully neuromorphic, vision-based autonomous flight. So we want event-based camera, some big spiking net, and then we want the outputs to go to the actuators of the drone. Now, we've been studying this for a large part in the context of optical flow landing. And I'm very grateful to Anthony for the previous talk, because he already showed that when this eagle goes down, things get bigger in the image, and there's this divergent optical flow. And that's exactly what honeybees use when landing on a flower. And they do this, really perfectly, even if there is like wind, and things do this very well. And I would like our drones to be able to do the same. And their strategy, like I said, is very elegant. And so let me explain it in the context of a drone. You have a drone, it looks down. If it goes down, then things get bigger in the image, and you have this divergent optical flow field. And if you calculate this mathematical quantity of the optical flow field, the divergence, it actually corresponds to the vertical velocity divided by the height. And these honeybees keep that constant. Now that means that if you're at 10 meters at 2 meters per second, at 5 meters you'll be going at 1 meter per second, and at 1 meter with 20 centimeters per second. And all of this without additional sensors like we engineers would put, like sonar or radar or LiDAR. The honeybee doesn't need this. And so we did this first with completely traditional elements like a normal camera, normal vision algorithms. But over the years, we've been introducing neuromorphic elements. Now, the first thing that we introduced was the event-based camera. So this, for us, is a pretty big drone, actually, because it had to carry this camera. And you see it on the left is going to make a divergence is 1 landing. And it's really pretty fast because all along the trajectory, it's always 1 second away from landing. And you see it in slow motion. On the right, you see the events. So the on and off events in green and red. In yellow, we used the local plane fitting algorithm for the optical flow, which we had to make much more efficient to run on board. Then we extract optical flow. And this was actually the first time that a flying drone was using the event-based camera in the control loop. And immediately it allowed us to do these really fast optical flow landings. So that is very promising, I think, for very fast control of drones. As I said, we were using local plane fitting to do the optical flow determination. But we want, of course, to do this in a spiking fashion as well. And this is what we did next. So we made a spiking neural network that you see here. The input is the raw events, and the output is actually neurons that fire for certain global flow field patterns. So we're moving to the right or the left with a certain velocity or down, etc. The cool thing is this network learns by itself to extract this optical flow. And it does so in different steps. So the first layer learns textural features, the middle layer learns local optical flow, and the output layer learns these global flow field properties, all with the same learning rule. It's a modified version of STDP, which we developed for this study, and we had to develop because of the event-based inputs. And the differences, why do they learn different things? It's all because of structural aspects of the network. So clearly here is like a pooling layer and a dense connection, so it learns these global flow field properties. But the reason that it learns local optical flow is that we introduced different time delays between these two layers here, and then it learns these different local flow patterns. So let us look at the results. So on the left, the inputs, and here textural layer starting to learn these textural features just by presenting it with event-based inputs. This is this unsupervised learning. So, and then in this MS-conv layer, you see that it learned local optical flow. So this is the rotating disk sequence. Here we have the events. Here we have a color coding for the different textural features. And here we have the optical flow, the local optical flow that comes out of it. Now the final layer indeed developed these neurons that fire for these global flow field properties. Here you see what happens if we move to the left and the right at different optical flow magnitudes. This fourth neuron is active when it's really fast. And then these are active less fast to the left, here to the right. These neurons are silent because they actually specialized for vertical motion in this case. Now, the next step, of course, the control. We also did in a traditional way, and we also wanted to do that in a spiking neural network. And actually, we implemented this in the Intel Loihi neuromorphic chip that Yulia was talking about, so that they developed. So we're very happy that we could use it. The drone does vision, it determines divergence, it encodes this in spikes, it goes into this chip, and then spikes come out that encode for the thrust that the robot should use for landing. In this case, we evolved the spiking neural network in simulation and then transfer it to reality. The divergence is encoded similar to how our spiking neural network would do it. The output are spikes for the thrust, which is decoded and then executed by a low-level controller to cross the reality gap. Furthermore, to cross the reality gap, we made the neural network as similar to the Loihi chip as possible. And finally, there's some things that you cannot foresee, like the initial height or velocity, delay or jitter in the sensor or USB key or whatever. This was randomized during evolution so that the solution would be robust to these changes. And this is the video. So the drone still looks a bit big because we needed this upboard to communicate with a chip, but I think in future versions you will be seeing it getting much smaller. And here is the optical flow landing. So this is a direct transfer from simulation to reality. So I must say, yeah, we're actually quite proud how well it landed. And this was actually the first time that the free flying drone was using the Loihi chip in the control loop as well. Now, to conclude my talk, yeah, I think that neuromorphic sensing and processing is a huge promise for insect-inspired autonomous flight of tiny drones. Of course, we're not there yet, so we want this fully neuromorphic pipeline. We want to improve learning mechanisms for spiking neural networks, and we want to tackle increasingly complex tasks. Because yeah, I didn't say that, so I said that we think it's important for like high-dimensional processing. I also think if you look at the repertoire of behaviors of insects, we're not close to that yet at all as well, so we also want to do that. These are the researchers that were involved in the neuromorphic work, and I thank you for your attention. I hope I'm kind of in time, and I'll answer your questions in the chat.
Thank you very much, Guido. Very interesting. And now to conclude this session on perception and action, we have Chiara Bartolozzi from IIT.
Hi, do you see my screen?
Yes, we can see it.
Okay, good. So thanks a lot. It's a very interesting workshop, and I'm really happy that I can share some of the work that we have been doing with event-driven sensors. And what I think we learned with this workshop is that there are really many things happening, really a lot of different flavors on how to use event vision sensors. Sorry, this is going. And so I'm going to show you what we did, and the message basically of this talk is there are a lot of things to do and a lot of different ways to do things. We need to find what is the best approach, and so we are looking at very different ways of using events. So the context of our work is humanoid robotics, and this is the scenario. Basically, we want to have autonomous agents, and the point is that they act in a very dynamic and unconstrained environment. So they have to interact with things that are moving. They are moving themselves, and it's nothing is fixed. We cannot put any constraint in how they can work. So what we want to do is to exploit the efficient information encoding of
Chiara, we lost you.
the sensors.
Chiara,
So the
Chiara, I
use
think,
is the
sorry.
neuromorphic ICAP. This is a platform for doing yes?
I think we lost 1 minute. At least I did. I don't know.
Ah, okay. Yeah, I just got a message that my internet connection is unstable.
Okay.
So.
Sorry to interrupt.
Yeah, no worries. Actually, there's the timing here in my presentation, so it's going by itself. It's kind of an autonomous presentation now. So I don't know what you heard, but basically the idea is we are in an unconstrained environment and we have to interact with dynamic objects. So event cameras might give us some advantage. And the platform that we use is the neuromorphic ICAM. So we integrated the ATIS sensors in the eyes of the robot. And so we have binocular event-driven vision. And now we also have frame-based sensors. So in case you are interested, we can also start integrating frames and events. At the same time, we have integrated different computational substrates that we can use to do this computation. So either using laptops or using FPGAs, and also event-driven computational platforms. So what can we do with event-driven vision on the ICAB? Well, first of all, we can decide if there's anything interesting in the field of view. And this has been presented already by Ralph very nicely. So to me, the job is easier. Attention is a way that biology uses to select interesting regions of the field of view and process them sequentially. So it's a way to improve the computational load. Another thing that we can do is to do feature detection. This is not very biologically inspired, maybe, but it's very much used in computer vision, where we detect features that then can be used for further processing. So, for example, we can detect corners and use these corners for doing stereo matching or for doing tracking and estimating motion in a point that is highly informative and can solve the aperture problem. We can then track things that we have detected. And in this case, we can really use the notion of the continuity over space of the event stream. So if an object moves from one pixel to the other, you immediately see the events moving from one pixel to the other. So it's continuous over space. And then what can we do with tracked objects? We can predict where they are going to be. And this is very interesting in robotics, because once you have, you're tracking something, you can predict where it goes, then you have time to plan the action for the robot and execute the action. So I'm kind of going to go very briefly through these examples, and I don't really have the time, but anyways, you can stop me whenever I don't have any more time. For the attention model, similarly to Ralph, we have been collaborating with Ansfried Niebuhr, and we use the concept of the proto-object model and the depth information. This is because a robot might be interested in something that could be an object, and that is close to the robot, so that the robot can interact with this object. So this is our implementation of the proto-object model using disparity, so as an information that is related to that. That comes from the work of the group of Ernst. And in this case, we, instead of using RGBD images, we use the events from the left and the right cameras on the robot. And to do so, we first create a disparity map using a cooperative stereo matching model that basically helps in computing the disparity in the image and removing the false correspondences of events that have to be matched between right and left cameras. And then we use the concept that Ralph has explained of the border ownership and grouping to detect proto-objects in the disparity map using the von Mises filters. So this is the result running on the robot. We have, well, Yulia, that is, moving her hands in front of ICAP, and that these hands, they switch disparity depth, basically. You have the stereo events, the resulting disparity map, where you can see that the color of the events changing depending on how close they are to the viewer, to the robot, and the corresponding saliency map, where you can see that the maximum, that is the red dot, shifts from one hand to the other when shifting to the closest hand. And this is what you can see here. The x coordinate of the maximum of the saliency map switches between the location of the right hand and the location of the left hand. And this is when the robot is not moving. But if we want to have the robot being able to perceive static objects, then we start wiggling the eyes so that we can also see the background events. And here you can see that the system is pretty stable. You only have peaks here in between that correspond actually to the face that of Yulia, because when the robot moves, also the face of Yulia is perceived by the cameras, and it really looks like a proto-object. So this is a way to use the sensors that is close to how biology works, and being fully event-based, we can, and we are, implementing this model on neuromorphic hardware. So The next thing I'm going to talk about is this more computer vision type of experiment, where we look at corners. So many different corner detection algorithms have been proposed in the literature that want to run online. With the new cameras, this is very difficult because the number of events that you get is increasing a lot. And so we need to find a way to have an online system that nevertheless doesn't sacrifice accuracy. So what you see here is the kind of the basic infrastructure or structure of the algorithms that were proposed for the corner detection. So basically you have the event stream, and for every event that you get, a data representation is computed. In this example, for example, that is the E. Harris corner detector. Basically, you have a small patch of an image where that is updated every time you get an event. And then there is a convolution with a Sobel operator, the computation of the Harris score, the application of a threshold that then decides, is there a corner or not? Is that an event belonging to a corner or not? And then you have the corner stream. This is completely asynchronous, it's event by event. But the problem is that the time of the computation depends on the number of events. And if you increase the throughput of events, then the system doesn't fulfill the real-time operation anymore. Different algorithms have been proposed to improve this. And basically, they act on improving the data representation and improving the algorithm by trading off accuracy to have something that runs faster. But it's still a lot depending on the number of events. So what we propose is to change the way the algorithm runs, decoupling the data representation update from the algorithm. So we have basically a data representation that is called the threshold ordinal surface that is very fast update for each event that comes. For each event that arrives, you put maximum in this image and you decrease the value of the neighbors, and then with thresholds. So whatever is far in time is goes to 0. And then the algorithm runs as fast as possible. It's simply an OpenCV call that runs on this novel data representation. And it runs as fast as possible on the most up-to-date representation of the data. And the output is a lookup table that gives the Harris score that is queried every time an event arrives. So basically, you still have a corner stream, you still have an asynchronous readout, but by decoupling the algorithm from the data representation, the algorithm can run as fast as possible, and it doesn't create delays in the pipeline, or the delays are very small. So here you see a video that compares our proposal with ARC and FAST. And if you see that, and this is with the new Artist camera, and you see that when the instantaneous firing rate increases, ARC and FAST, they have very high delays, and you see that they are not synchronous anymore with the input events, while the LUV harness corner are still synchronous with the input. So this is kind of telling us that depending on the data representation that we use, we can improve how fast the algorithm can run. So I'm not going to touch on.
I think we are running out of time. Yeah, Chiara.
Okay, I'm just going to the last slide. Let me skip this. Okay, so the message I wanted to give you here was we can have very different ways of computing with events, but the story is not just restricted to vision and computation. There are other things that we can do with event-driven sensing. For example, using auditory sensing that can be used, for example, for sound source localization, auditory attention, and audiovisual speech detection and speech recognition. It's also very important to use tactile sensors because touch is really localized in space and time. And so the message here is it's really an exciting framework, and vision is, you know, moving very fast, but there are really a lot of interesting things that we can do. I'm done.
Thank you very much. Okay, now we are open to the questions. I think some of you are already answering the questions in the chat. Yulia, about one-shot learning. So let me go for one of the questions that it's not answered yet. Chiara, what is the main motivation for using event camera instead of frame camera for attention? And how do you plan to use these attention maps?
Right. There are different motivations. First of all, as I said, the use of event cameras is more general, right? We want to try to use the low latency and have a system that runs very fast. For example, in our scenario, we have the eyes of the robot that can move. And we can have events and frames, and we use a system where we have a beam splitter with event-driven cameras and frame-based cameras that have very, very high resolution, and they are RGB. So what we want to do is have a very low latency, real-time attention system that gives you a region of interest. Saccade to that region of interest and foveate, you know, using the concept of fovea. And then we can use a crop of the proto-object that we have on the RGB and the event to have object recognition, for example, or, you know, to have a better perception of the specific object we want to interact with. And this is one motivation. The other motivation comes from my passion of looking at biologically inspired computing. And, you know, when you see these models inspired on how the brain works and that they take RGB images as input, well, if we have an input that is more similar to the output of the retina, even if it's loosely inspired on retina, it makes a bit more sense and we can learn something more. For example, one thing that we learned was that, well, the event-driven sensors, they already do edge detection, so you don't have to do that in the model. You can simply skip that because you already have the edges. So you can avoid the center surround, for example, computation there. I guess I already answered to the how do you plan to use this attention?
Yeah, it's good. Thanks. More questions?
Okay. So maybe let me raise some panel questions since we have a few minutes to all of you. Where do you see the greatest impact of neuromorphic computing with spiking hardware in the near future? And especially where do you see the advantages of these spiking neural networks also in task performance?
I could answer that from my perspective. So I personally believe that robotics is one domain where neuromorphic computing is very promising. And one maybe superficial argument is that spiking neural networks have evolved in biology in order to control movement in real world dynamic environments. So we definitely have something to learn from that. And as robotic systems move to real world environments where they deal with a similar problem and they have to control movement safely, in an adaptive way, control soft actuators. I think these type of networks that are sparse, efficient, but at the same time powerful in terms of representation, and that can be updated on the fly, they can really bring large advantages. Another domain where we see interesting good results is optimization. So if you think, we just have seen some good numbers in application to constraint optimization problems. And if you think of that, many problems that the brain is solving are kind of like constraint optimization problems, right? You want to optimize your behavior, you can have some cost functions that determining how you solve your problems. You have different constraints. They can be just physical, dynamical, mechanical constraints. Your current environment sets some constraints. And then, so we found these spiky neural networks, they solve these problems by exploring the dynamics stochastically. And we find huge advantages compared to conventional hardware. So these are, from my personal perspective, don't take it as Intel's opinion. We explore all kinds of applications. But these are the two.
That's very interesting. So you have specific examples. I know the lasso algorithm, I think. No.
Or Sudoku constrain satisfaction problems that are discrete, with discrete state space and binary constraints. This is the example that we have has been shown in Manchester lab actually first, and then the postdoc joined us as well. And you just see the scalability is nice. And you can see how that happens, right? We can, like in this massively parallel well, sample the state space efficiently instead of going through possible states sequentially.
I would like to ask
I may add to this question. Sorry to interrupt. I think I can add a couple of things. One is what Bernabe has mentioned, that is the pseudo-simultaneous computation, right? If you have a system that can give you very quickly the output as soon as you integrate enough information, that's very useful in robotics and in any system that has to react in real time. And the other thing that we have not touched, because we are not there yet probably, is adaptation and the possibility to have systems that run continuously, that can learn continuously, and that can adapt to different environments, to different situations. This is, I think, one of the main driving forces that basically motivates us to try to use neuromorphic hardware and spiky neural networks.
I wanted to ask in this session, so all of you have a practical experience in joining perception and action with neuromorphic hardware. So what are the difficulties and the challenges there? I mean, Yulia defined the chip as a research chip, not a product. So I guess that's a bit.
I could.
I think Guido can say even more, but I can also
say something about it. So, what Yulia also said is that currently, for example, so like I said in my talk, so we do see that in perception, and processing of high-dimensional visual inputs, it would be nice. The current chips, though, don't have that many neurons and connections yet. This is improving as we speak, right, Yulia? So that's positive news. Yeah. And the second thing is, because it's not a product yet, in order to use it, it's not easy, of course. So that's why, for example, Intel within the INRC, they're working with many parties together to try and start using these chips. And then hopefully when it is a product, it will be easy to use. But currently that's a challenge. And I think connecting a little bit to the last question, you saw the drone that was doing the optical flow landings in the end was actually pretty big for our standard. And that's because from a system perspective, just to interface with the chip, we still needed, for example, this upboard. So I think also there, and this progress is being made, by the way, but in order to be really useful, it really needs to deliver this energy efficiency also from a system perspective. And that we're not there yet, but actually we're betting that parties like Intel and others are going to get there. And so, so these are some of the difficulties. And to connect to what Chiara said, the learning aspect. So learning these networks, I hear that, the temporal processing is important in spiking networks, but personally, I didn't really see this yet, evidence that this has worked better really in spiking nets, to be honest, but please correct me. There's the big experts in the field are here today, so put it in the chat if you want. But I think we really have a long way to go in terms of learning and actually exploiting those temporal properties of the spiking nets.
Yeah, adding on to some of the points he was making, I definitely agree. One of the big things with these perception action systems in terms of latency and also realizing the power utilization benefits is the glue between all of these things. It's going between an event-based camera over a USB interface to some CPU to do something. It's really the tight integration of trying to put these things together that we've at least noticed does make a difference in terms of your USB latency might be something like 4 milliseconds. So if that's in the end, you're looking at this fast motion applications, that may be important for you. Also, to realize the power utilization benefits, it's also important that a lot of the energy is spent sending a lot of this data off chip. If we actually want to save the energy we have, we need to figure out what are the actual algorithms near chip that we need to run that are important and that can possibly summarize or make our data intelligible for perception later on, or just send it straight to planning and acting. It's definitely an open area of research and definitely a very exciting area at the moment.
I think from my perspective, everything has been said, right? So I can only summarize, right? Systems and input output is important. Throughput, how can we get the data on chip and read it out quickly with low latency and high throughput? Algorithms, starting with signal representation, how to efficiently represent signals with this threshold-based sampling, event-based sampling. There are some challenges, right, in terms of signal representation or signal sampling. What does it mean that the signal is now sampled in this particular way? So I think some theory needs to be developed there. And then simply, algorithms, how to solve different problems, the neural network, where to come up with structures, how to use learning, that online learning. If we have this online learning and adaptation, many challenges arise, right? Keeping system stable and robust, how to control the learning process becomes a challenge in its own sake. Seeing what is happening on chip, I think, is a challenge, right? Because the chips are usually not built for you to easily access every value. If you do that, you'll slow down the whole system. But for debugging, for development, for understanding what is happening on chip, that's important. And that goes into many practical challenges, the software frameworks, tools to use, so how easy it is to develop a network and then the whole system and debug it, see what's happening where. Yeah, these are probably the main challenges.
Thank you. Yes, I think there are still many challenges and like a long way ahead, and that's good news. Good things to do research, right? I think Yulia mentions one, or I think in the video somebody, Riyad also mentioned in his video, I think that you have to also train the new generations of engineers to be more like a mixture of engineer and neuroscientists to be able to design those new algorithms, right? It's always difficult to program this neuromorphic hardware.
Yeah. Yeah, so very often so people might just lack some, because you need to be an expert in computer vision, machine learning, deeply understanding the math, neurobiology, systems engineering, design, robotics. Yeah, that's challenging, and ideally have deep knowledge in every field.
One last question before we move on to the next session, if I may, is if you are able to tell us about the roadmap, when will this change from being a research chip into a product that, we can buy event cameras, but we cannot buy neuromorphic hardware yet?
You cannot. So I will,
well, at least not the Loihi, right?
Sorry. Yeah. So it's a research chip. Everyone here can use our chip, right? You just have to join our Intel neuromorphic research community. That was one slide that I tried to flash. So the neuromorphic chips, they tend to be expensive today, right? So and there's some fundamental reasons why they're expensive. So this cool feature that memory is collocated with processing makes the systems expensive. So this type of memory is just not very cheap. So you can imagine the applications where we will see them are probably not consumer applications where you will have like billion devices sold very soon. So that would be either some very high-end applications where people are ready to pay a lot of money for exotic hardware and also going through the pain of fine-tuning them. This is where maybe Intel could be interested in some products. Otherwise, there could be some niche applications here and there where you don't sell a million or a billion of devices. And there probably small companies have bigger chances to bring devices on the market because they will be happy if they sell, I don't know, 100,000 of their devices. Intel probably won't be that happy if that's only that number. So we, at Intel, we depend on large scaling up of this technology, that we will find some application where the advantages are so huge compared to conventional technology that, wow, that's very, very promising. But smaller companies and startups, of which there's plenty right around them, they have maybe a better chance to bring this hardware, over the threshold of being a product. Yeah, and we need help, right, from everyone in the community, helping to, at least detect what is missing. right? So if people are not using, if there is a clear formulation of what is missing, then one can act on it. If it's just dismissed, then it's more difficult to act on it.
Good. Well, thank you very much. Thank you to all our speakers in the third session. And now we move on to the fourth one, which is led by Kostas Stanlidis.